Okay, we are going to take a look at this next section of thermochemistry called enthalpy changes. And essentially in this lesson, we are going to look at a few different ways on how we can record and express our changes in enthalpy. Now, essentially, we're looking at this for a variety of different reactions, and that can be anything from formation to combustion and anything in between. So, essentially, there's 4 ways to notate or communicate enthalpy changes. The first is by stating molar enthalpy of a specific reactant in a reaction. Okay, so we can look at the molar enthalpy. Now again, molar enthalpy is the enthalpy per 1 mole of a specific reactant in a reaction. Okay, we can state the enthalpy change of a balanced chemical reaction. Okay, we can include that energy value as a term in our reaction, and we can draw a diagram. Okay, a chemical potential energy diagram. Now, potential energy is key there. So there's 4 different ways, and we're going to go through each of these ways in a little bit more depth so that you get a better understanding of what these 4 things are. Okay, so the first one, the first method is by understanding the molar enthalpies of a reaction. Okay, now this is determined empirically, so in a lab setting, from energy released or absorbed per unit of chemical amount. Okay, again, so we're doing per mole to from the surroundings at a constant pressure. So our standard enthalpies are always at SATP, and meaning that we can notate it by this little standard sign or the degree sign. Okay, so this is method 1, this little section in sort of this turquoisey color, and it's kind of confusing because it's what does all of this mean? We have a variety of symbols and letters, and it's all for one single variable. So essentially what it means is we have our delta sign. Now our delta sign is in reference to a change. So again, anytime that you see that little triangle, we're talking about a change in enthalpy. Okay, now our delta H is our change in enthalpy. Okay, this little r here is our reaction type. So a reaction type could be, it could be combustion, it could be formation, it could be decomposition. Basically any type of reaction. Now, essentially, we notate the reaction type by the letter that reaction starts with. So we could do delta C for combustion, or we could do delta F for formation, or delta D for decomposition, etc. So this just means the change in enthalpy for whatever reaction type that we have. This just means molar. This little m here means molar. So in other words, per 1 mole. Okay, the standard state means that we're at a standard temperature pressure type thing, and our substance is going to be the entity that we're looking at. So in this case, in my example, we're going to be looking at our methanol. Now we're going to look at the combustion, formation, and just a general reaction of methanol, and look at how this value changes and how it numerically changes as well. So for our first reaction, we're going to look at the formation. Again, this little f means formation. So we're going to look at the change in enthalpy of formation, the molar formation of methanol. So that's what this little symbol tells us. Now, a formation reaction is a reaction where we have the creation of a compound from its constituent elements. So our reaction would be carbon, because we have a carbon in methanol, plus hydrogen, and we have hydrogen gas, plus oxygen. Oxygen gas gives us methanol. Now, if we look at how to balance this, we need 2 hydrogens, and because we have O2, we actually need 1/2 of O2 to correctly balance this for 1 mole. Again, because this is a molar enthalpy, we want for 1 mole of methanol, which is what we have like this. That's why I have to use a fraction to balance my oxygen. Now what we see here is for the molar enthalpy of formation of methanol, we see that this value equals negative 239.2 kilojoules per mole. Okay, so we see that there's 239.2 kilojoules of energy released, because it's a negative sign, it's exothermic, per mole of methanol created. Okay, so we see this value here for our formation reaction. Now, if we jump and take a look at the combustion of methanol, we're going to get a slightly different reaction, well, a very different reaction, and a different molar enthalpy here as well. So again, because our little c is notating that we have combustion, okay, I am going to have my reaction of my combustion of my methanol. So I have my CH3OH. I have to combust using oxygen. And I always create CO2 and H2O. And we're going to assume that these are all gases and vapors here. Okay. And this is a liquid. Okay. So for every 1 mole that we combust, we get 2 moles of water vapor, 1 mole of carbon dioxide, and we use 3/2 of an oxygen for this, for 1 mole. Okay, again, if you need to slow down and take more time to balance that, there's no problem. I'm just doing the balancing a little bit quicker so we can get to the enthalpy portion. So what we see is when 1 mole of methanol, again, we need the molar values. Okay, so when 1 mole of methanol is combusted in oxygen, producing carbon dioxide and water vapor, we see that there is negative 725.9 kilojoules per mole of energy produced. So we have 725.9 kilojoules per mole of energy produced. Again, it's a negative value, meaning that it's exothermic, for every 1 mole of methanol that is burned. Now, if we look at just like a general reaction of using or producing methanol, but in a different method, okay, we can look at this reaction. We can look at the reaction of carbon monoxide and hydrogen gas. Giving us a product of methanol. Again, we have 1 mole of methanol produced, and we have to use 2 moles of hydrogen gas and 1 mole of carbon monoxide to produce this methanol. Now what we see for this value is we see that in this reaction, again, this value is determined empirically in a lab setting, okay, we would see that this creates or produces 128 kilojoules per mole of energy. So you can see that by notating our molar enthalpies, either formation, combustion, or any other reaction, we can still look per 1 mole of methanol produced that we see in each 3 of these reactions, but we have a different molar enthalpy depending on the style of reaction. And by notating that this is formation, combustion, or just a general reaction, we can be specific as to what we're looking at. Okay, so that is method number 1. Method number 2 is recording enthalpy changes beside a chemical equation. So for this example, we can look at carbon monoxide plus our 2 hydrogen gas. This is the example that I had in the previous slide there, that it forms methanol. Now again, we can just notate this as the enthalpy of reaction as being negative 128 kilojoules. Okay, now in this case, it is kilojoules per mole because we only have 1 mole produced. But if we were to just look at this reaction in particular, now I could change how I balance this, and then this amount of energy would change. But based on this reaction, this is the amount of energy that is produced in this reaction. Again, because it is a negative sign, this tells me that it is exothermic. Okay, we can calculate these molar enthalpies, and the actual chemical amount of the reactants and products will change the enthalpy of the reaction. So if we take an example and take a look at our example of sulfur dioxide. Okay, I can take a look. Now, do I have my reaction here? I do. So we see that sulfur dioxide and oxygen react to form sulfur trioxide. Okay, so the standard molar enthalpy of combustion of sulfur dioxide in this reaction is negative 98.9 kilojoules per mole. So what is the enthalpy change for this reaction? So if we look at this reaction here, we see that we have 2 moles of sulfur dioxide. We have 1 mole of oxygen gas giving us 2 moles of sulfur trioxide. So if I remember my equation that says that my change in enthalpy, and in this case it's my change in enthalpy of combustion of this reaction, it equals my moles times my molar enthalpy of combustion. So because my molar enthalpy of combustion for this reaction is equal to negative 98.9 kilojoules per mole, and we see that in our equation we have 2 moles of sulfur dioxide, we're going to multiply that by 2. So I get a value for this equation to be 197.8, negative 197.8 kilojoules. Now again, it's not kilojoules per mole because now I've multiplied it by 2 moles, so my moles actually will cancel out when I do this calculation. So when I write my net overall equation, and if I'm recording it based on method number 2, I would write 2SO2 plus O2 gives me 2 SO3s, and my enthalpy of combustion for this reaction is equal to negative 197.8 kilojoules. So that is how I would record my reaction using method 2 by recording my enthalpy change right beside my reaction. Now, if I was to say look at this value for 1 mole of SO2, so let's take a look at how that reaction would look. We would see 1 mole of SO2 plus half a mole of oxygen gives us 1 mole of SO3. Now again, because I am looking at per mole, instead of multiplying this value by 2 moles, I'm going to multiply it by 1 mole. Now in this case, I'm just multiplying by 1, so my value for this reaction is actually just 98.9 kilojoules. And again, it's not kilojoules per mole, I've multiplied it by 1 mole. So this would be my reaction if I had 1 mole of SO2. Now notice the difference is that I've changed the way I've balanced this, and by the same factor that I've changed the balancing, I've changed my enthalpy of combustion when I record it on the side. Okay, now this would all be written in sort of one straight line, which you'll kind of see in my examples here. And that's just to notate the change in enthalpy for that specific reaction. Okay? So let's take a look at method number 3. Okay, we can record our enthalpy changes in our balanced chemical equation. So we have to consider our chemical equations sort of in 2 separate categories. We need to think of it first as one category being endothermic and the other category being exothermic. So if a reaction is endothermic, it requires energy to react. So we know so far that generally if we see a positive value, okay, if we see a positive value, that means that we need energy and we have an increase in potential energy, but energy is required to react. So what we do is we add energy as a reactant. So we put this energy in as a reactant. Now, in this case, we have the decomposition of water, and we see that with a mole of water, we need to add 285.5 kilojoules of energy to form our hydrogen gas and our oxygen gas. Now, again, this is energy that needed to be added. If we look at an exothermic reaction, we know that it produces energy. Now, again, we write this energy this time as a product. So we have the formation of magnesium oxide. So we have magnesium plus half a mole of oxygen gas gives us magnesium oxide and 601.6 kilojoules of energy. Again, if we record an endothermic, we write the value as a reactant. If we look at an exothermic, we record it as a product. And again, this is a negative value. We see these values recorded as a negative enthalpy or a negative potential energy. Again, because we are losing potential energy, but we have this much energy released as heat. Okay, so we have to be careful as to how we're thinking about this. Now notice, when I record my values, I do not record whether it is a negative or positive value. Even though we know that exothermic reactions are negative values when we record them, okay, when we plug it into our equation here, by recording this value on the product side is the same as indicating it as a negative enthalpy. Okay, so we do not ever record, when it's in our equation, we do not record that as a negative 601.6. Okay, we record it just as the absolute value, but by putting it on the product side indicates that it is a negative value. So if I was to write out my equations here with method 2 below, I would write down that my reaction would look something like this. Okay, this is a positive 285.5 kilojoules. And in this bottom reaction, I would see that Mg plus half of an oxygen and my enthalpy of reaction for this guy is equal to negative 601.6 kilojoules. So be careful when you're going through and recording these values. We always write the absolute value, and again, the product notates that it's a negative, the reactant notates that it's a positive enthalpy value. Okay. Our fourth method that we can take a look at is our enthalpy change diagrams. Now, this is a visual representation of a chemical reaction, and again, we need to sort them based on our exothermic and endothermic reactions. So we have our exothermic on the left and our endothermic on the right. Now I'm going to take a look at our exothermic first. Again, note that this is a potential energy diagram. We have our potential energy on the side. So if we think of this as a change in enthalpy, we have a great deal of potential energy, okay? We have a great deal of enthalpy, you could call it, in our reactants. Now, our change in enthalpy decreases. We lose potential energy from our reactants to our products. Now, again, this energy doesn't simply disappear. This energy turns into heat energy. Okay, it's released as heat. Now, if we talk about potential energy of our exothermic, we start with our reactants up high and our products down low, and we lose that potential energy, but again, any energy lost is gained as heat. If we look at an endothermic, it's the inverse. We see that our reactants are down on the bottom here. We gain, again, it's potential energy that we're looking at. We end up gaining potential energy, okay, but this energy can't just magically appear. We had to input heat energy. We had to input heat to get our products formed. So from our reactants to our products, we gain potential energy. We have a positive enthalpy. Okay, we gain our potential energy, positive enthalpy. Okay, so there's these two general diagrams that we can look at when we are looking at our method number 4 and drawing out our products and reactants. Now, I'll take a look at another example. I'll take a look at an example on how to show this. But in general, one thing that you'll be doing when you do these diagrams, and I'm just going to switch to a little bit more solid of a color, you would actually write the reactants here and the products here. So when you would do this, if I'm taking my example from my previous page, if I think of this as an exothermic, I would write my magnesium plus my oxygen, okay, and I would get my magnesium oxide formed. And the change in heat, I would actually write equals, or the change in enthalpy equals negative 601.6. Okay, there we go, 601.6 kilojoules. So I would record this. I would actually, instead of writing the word reactants and products, I would record that these are my reactants, these are my products, this is my change in enthalpy. And if I had values for each of my reactants and products, the enthalpy of these things, I would record those values on the side for a scale as well. Again, if I think of my endothermic reaction, I would again use my water as an example. I need to input this energy to get my hydrogen gas and my oxygen. And again, I would record this enthalpy. Of course, I don't remember that value. 285.5, and this is positive 285.5 kilojoules. Again, we're inputting that energy, so we're gaining that enthalpy in the end. Okay, so I would be very specific when you're writing these things in, when you're writing in your reactants and products. Be specific. Don't just use the general words reactants and products. Okay, so a summary. In an endothermic reaction, or an exothermic, in an exothermic change, your molar enthalpy of reaction is going to be less than 0. Again, it's going to be a negative value. Okay, in an endothermic, it's going to be greater than 0 or a positive value. In an enthalpy change, if your reactants go to your products, again, your enthalpy is going to be less than 0, negative value, and this is going to be a positive value. When we write this in a balanced equation, we write energy as a product when it's exothermic and energy as a reactant when it is endothermic. Now in our potential diagrams, potential energy diagrams, we see that our potential energy of our reactants is greater than the potential energy of our products, again resulting in a negative enthalpy. And in our endothermic, we see that our reactants have less energy than our products, meaning that it gains potential energy and we have positive enthalpy. So our summary example, it says that energy is transformed in cellular respiration and photosynthesis. Now I'm just going to switch my colors here. So we see that energy is transformed in cellular respiration and in photosynthesis. Cellular respiration is a series of exothermic reactions. Okay, so I'm just going to write that down at the top here. Cellular resp. Now, if you've taken some biology, you might know this already, but if you haven't, then this might be a little jog in the memory. Okay, so cellular respiration is exothermic, and photosynthesis is endothermic. Okay, so we see that we have an endo and an exothermic reaction. Okay, and we said express the standard enthalpy changes for cellular respiration and for photosynthesis by using the 4 different methods of communication. So we have a variety of ways that we can record these values, and we are going to go through solving that for both. So let's take a look at our example here, where we have 1 mole of glucose consumed during cellular respiration to release 2,802.5 kilojoules of energy. So we're going to take a look at this example first. So in method number 1, and I'm going to try and break this down here. So we have method number 1, where we have our standard molar enthalpy of for cellular respiration of glucose. Now, because again, we have cellular respiration, which we said is an exothermic reaction. Okay, we essentially just write this down as the molar enthalpy of reaction, okay, is equal to negative, because it's exothermic, and because we're only looking at 1 mole, we can automatically record this value as a molar value. So we can record 2,802.5 kilojoules per mole. Now the one thing we're missing is that we need to record this as C6H12O6. So we need to look at this for glucose. So this is the first method of recording our changes in enthalpy. Our second would be by looking at the overall chemical equation. So we have we consume glucose. So we're looking at how we burn glucose. So we have C6H12O6. We have oxygen gas. Again, essentially, cellular respiration is just a controlled form of combustion, and it's in any sort of living thing that performs some level of cellular respiration. And we produce carbon dioxide, and humans do this, so you should know that we produce carbon dioxide, we breathe out carbon dioxide, and also a metabolite of breaking down some sugars is water. Now again, if you were to think of having heavy amounts of exercise, you would be breathing out lots, and you'd also probably be producing some water as sweat. So we can think of that as we go through. Now we have 6 of these and 6 of these to have our proper balanced reaction. Now to continue this method, we need to write down that our enthalpy of reaction, again, this is for our 1 mole, is equal to negative, gotta squish it in, kilojoules. Now in this case, I'm not going to record kilojoules per mole because I could change this value based on the reaction and based on the balancing. So I record that as just 2,802.5 kilojoules for this reaction. Now, method number 3, if I take a look at method number 3, essentially it's the same equation. Except this time we're going to record our enthalpy as a value in our equation. So since this is exothermic, we're going to record this value as a product. So we're going to add our 2802.5 kilojoules. Again, you do not record it as a negative value because by putting it on the product side, that automatically indicates that it is a negative enthalpy or that energy is released. Okay, our fourth and final way to record our enthalpy, if we look at a potential energy diagram, like so, again, I would write EP, okay, and this is going to be in kilojoules. And this is just our reaction as our reaction goes on. It doesn't need to be too specific. We have our reactants. Actually, I'm just going to make this a little bit bigger. And we have our products. Now this value here is going to be our change in enthalpy. Oops. Let me just make that a little straighter. Perfect. So then I'm going to record my reactants, which is my glucose. Notice that I'm writing down the balanced reactants. I need 1 mole of glucose and 6 moles of oxygen gas, and I produce 6 moles of carbon dioxide and 6 moles of water vapor. Again, we assume that it's, well, in this case, we're probably producing liquid water because it's in a human system, or it's in a living system. Okay, and again, I would record my enthalpy value here to be negative 2,802.5 kilojoules. Okay, so again, I would record this value on the side here. I show that my change in enthalpy with my reactants and my products. Okay, so we see a negative enthalpy change. Now, if we take a look at our photosynthesis reaction, we're going to do all the same steps. I'm going to go through these a little bit faster now that we know how to do them. So for photosynthesis, if we look at our enthalpy of reaction, our molar enthalpy of photosynthesis, now again, in this case, we're producing glucose. We're producing this entity. Now, in order to produce this, we know that photosynthesis is endothermic. So because it's endothermic, I have a positive value, and I'm producing, or I am producing this glucose, and so I need to input my 28O2.5 kilojoules, and that is per 1 mole of my glucose produced. Now if I take a look at method number 2, recording this as a value in my reaction, I have the inverse. I have 6 carbon dioxides, 6 waters, I have 1 glucose, and I have 6 oxygen gas produced, and the change in enthalpy of this reaction is equal to positive 28O2.5 kilojoules. Okay, again, because this is endothermic, I'm recording my values as a positive. Take a look at method number 3. Again, because this is an endothermic, I'm going to include my energy as a reactant in this chemical reaction. So I'm going to add my 28O2.5 kilojoules. Again, I don't need to notate the sign on this value because notating it as a reactant is indicating it's a positive, giving me C6H12O6 and 6 oxygen gas. Okay, so again, I've notated it as a reactant. And method number 4, we see our, I better draw a bigger line here, our graph, we see our potential energy again in kilojoules. This is our reaction down here, and we see that we start with our reactants. We have our products. We have a change in enthalpy of this reaction to be positive 28O2.5 kilojoules. And we see that we produce our glucose. And we use up our carbon dioxide and water. Again, notice that everything in my chart here, or my graph, is balanced so that I know how many moles of each of these entities that I am dealing with. Okay, so hopefully that is clear on the 4 different methods on how to record our changes in enthalpy. Now, I would say that if you are not sure about a few of them, you might want to go back now and just ensure that you're understanding the differences between the 4 methods and just be familiar. Essentially, you won't be tested specifically on each type, but either in my assignments or with the diploma, they can potentially, they can give you any one of these 4 ways of recording enthalpy changes, and you will have to apply that knowledge to a question. So definitely be familiar with these 4 methods and know definitely the difference between your endo and your exothermic reactions. Now, at any point, if you need to pause and go back, I suggest doing that now, and good luck.